Welcome to Papers Simplified, a podcast brought to you by SILMA AI. We break down, cutting-edge research papers in AI.
Yeah, we try to take those complex ideas and make them clear and insightful, even if you're not like, an AI expert, right?
Exactly. And today we're diving into Can 1B LLM Surpass 405B LLM? Rethinking Compute-Optimal Test Time Scaling. It's a fascinating paper that explores how smaller AI models can actually outperform much larger ones.
It's kind of like, David and Goliath
Right.
in AI world.
Exactly. So let's maybe start by defining test time scaling, or TTS. It sounds complicated, but the idea is pretty straightforward.
Yeah, you got it. Test time scaling is all about giving an AI more processing power or time to think during a task. It's like giving a student extra time on a test, right?
So instead of just relying on the AI's initial training, we're
Yeah.
giving it a little extra boost during the test itself.
Precisely. And there are two main types of TTS, internal and external. Internal TTS is like training the AI to think more slowly and carefully from the start. And external TTS involves using additional techniques during the test to enhance performance.
Interesting. So where does this paper fit into all of this?
So this paper focuses on finding the most efficient way to scale compute for a given task, an AI model, what they call the compute optimal TTS strategy.
So it's not just about like throwing more computing power at the problem. It's about being smart and strategic about how we use it.
Exactly. And the authors argue that previous research didn't fully consider all the factors that, impact the effectiveness of TTS.
Okay, so what are those key factors?
Well, you have, three main components at play. First, there's the policy model, which is the AI that's actually trying to solve the problem, right? That's the brains of the operation.
Got it. What's the second factor?
Second, you have process reward models, or PRMs. These are AI models that act as judges, evaluating how good the policy model solutions are. They're like coaches who assess the athlete's technique.
So they're not coming up with answers themselves. They're just judging the policy model's work.
Precisely. And finally, you have the problem difficulty itself, right? Some tasks are just inherently more complex, and that needs to be factored into the TTS strategy.
That makes sense. So how does this paper propose we approach TTS differently?
Well, they introduced this idea of reward-aware TTS. Previous research often used a single PRM to evaluate the policy model, but this paper highlights that, different PRMs might be better suited for different tasks.
So it's like judging a chef based on their gardening skills.
Sure.
The PRM might not be evaluating the right thing.
Exactly. Reward-aware TTS adapts the scaling strategy to the specific PRM being used. This makes the system more accurate and efficient overall.
This all sounds very complex and nuanced.
It is, and we're just scratching the surface here. The paper also delves into, how we measure problem difficulty. Instead of relying on quantiles, which can be misleading when comparing different models, they propose using absolute thresholds based on the model's accuracy.
So instead of ranking problems based on how well a particular model does, we're looking at how solvable they are in general.
Exactly. It's a more objective way of assessing difficulty. And with these new ideas in place, the researchers conducted a series of experiments to test their approach.
This is where it gets really interesting. What kinds of experiments did they do?
So they tackled, some challenging math problems using two data sets. Math 500, which consists of 500 tough high school level math problems, and AM24, which is based on problems from a highly competitive math exam.
So they really put these AI models through their paces.
They did. They used a variety of models from the Llama 3 and Qwen 2.5 families, ranging in size from a tiny 0.5 billion parameters to a massive 72 billion parameters. And they also tested their approach with, several different open source PRMs.
So they had a lot of variables to play with. What were some of the most surprising findings?
One of the most significant findings was that using their compute optimal TTS approach, a smaller 3 billion parameter model was able to outperform a much larger 405 billion parameter model on certain tasks.
Wow, that's a huge difference in size. So smaller models, when given the right tools, can compete with the giants.
Absolutely. They also found that the best TTS strategy varied depending on the specific policy model, the PRM, and the problem difficulty. There's no magic bullet. It's all about finding the right combination of factors.
It's like fine-tuning an engine to get the best performance.
Mm.
So what does this tell us about the future of AI development?
Well, it challenges the assumption that bigger is always better. Maybe we don't need to keep building larger and larger models. Instead, we can focus on developing, smarter algorithms and strategies that allow us to get the most out of smaller, more specialized models.
That's a pretty radical shift in thinking.
It is, and it opens up, a lot of exciting possibilities. Imagine a world where smaller research teams and companies can develop AI systems that are just as powerful as those created by the, tech giants.
It would be amazing. It would democratize AI and lead to even more innovation.
Exactly. But let's not get ahead of ourselves. We still have a lot to learn about TTS and how to, best implement it.
You're right. It's a complex and fascinating topic. Before we move on, let's take a step back and make sure we've covered the basics. We've talked a lot about how effective TTS can be, but how does it actually work in practice?
That's a great question. There are several different methods researchers are using to implement TTS, each with its own, strengths and weaknesses. Let's dive into those next. So let's unpack some of these, TTS methods. One of the simplest approaches is called best of N, or BON.
Okay, Bond. That rings a bell.
Yeah.
Remind me how that works again.
Yeah, it's pretty straightforward. The AI model generates multiple solutions to a problem, and then we use a scoring system to pick the best one. Think of it like trying to hit a bullseye. You take several shots, and the one closest to the center wins.
So it's like a kind of a brute force method,
Yeah.
trying a bunch of different options and seeing which one sticks.
Exactly. Now, another common method is beam search. This one's a bit more strategic.
How so?
So imagine you're navigating a maze, right? Beam search explores different paths, but it keeps track of the most promising ones, right? And discards the dead ends. This way, it focuses its effort on, finding the best route.
That makes sense. So it's more efficient than just randomly trying every path.
Precisely. Now, the researchers also explored a more advanced technique called diverse verifier tree search, or DVTS.
DVTS, that one sounds intense.
It builds on beam search, but it adds a layer of diversity, right? Instead of exploring just one main path, it branches out into multiple subtrees, each with its own beam search.
So it's like having multiple teams searching the maze, each with a slightly different strategy.
That's a great analogy. This diversity helps ensure that the AI considers a wider range of potential solutions, which can be really helpful for complex problems where the best answer isn't obvious.
So which one of these methods is the best?
Well, that's the thing. There's no single winner. The researchers found that the optimal method depends on, several factors, including the policy model, the PRM, and the problem difficulty. It's all about finding the right tool for the job, right?
It seems like there's a recurring theme here. It's not about finding a one-size-fits-all solution. It's about carefully considering all the variables and tailoring the approach accordingly.
You got it. Now, while exploring these different TTS methods, the researchers made some interesting observations about the limitations of PRMs.
Oh, right. The PRMs, those AI judges
Yeah.
that evaluate the policy model's answers. You mentioned earlier they could have their own biases.
Exactly. And those biases can, impact the results, even with TTS in the picture. For example, some PRMs tend to favor shorter answers, even if they're not as accurate.
So it's like they're rewarding brevity over substance.
You could say that. And this can be a problem if the task requires, a detailed and nuanced solution. They also found that the way you combine the PRM evaluations can influence the final answer, right? Different voting methods can lead to different outcomes.
So even the seemingly simple act of, choosing the best answer adds another layer of complexity.
It does, but that's the nature of, AI research. It's full of intricate details and unexpected challenges.
And those challenges are what make it so fascinating.
Yeah.
Speaking of challenges, one of the most exciting aspects of this research is how it challenges the traditional bigger is better mentality in AI.
Absolutely. This paper provides compelling evidence that we don't necessarily need to keep building, ever larger models to achieve breakthroughs. Smaller models, when enhanced with the right TTS strategies, can be incredibly powerful.
And this could have a huge impact on how we develop and deploy AI in the future.
Imagine a world where AI is more accessible, not just limited to organizations with massive, computing resources.
That would be incredible. It would truly democratize access to AI and unlock a whole new wave of innovation. Okay, before we get carried away with future possibilities, let's take a moment to compare TTS to other techniques for enhancing AI performance. How does it stack up against, approaches like reinforcement learning or knowledge distillation? Those are great points. It really seems like TTS could be a real game changer. But how does it compare to other approaches like, reinforcement learning or knowledge distillation?
Yeah, that's where things get even more interesting, right? The researchers did compare their compute-optimal TTS strategy to those other methods.
What did they find?
Well, TTS proved to be more effective than both direct reinforcement learning, where the AI learns by, trial and error, and imitation learning, where it learns by mimicking solutions provided by humans or other AIs.
So it's a more efficient learning strategy than those more traditional approaches?
It seems so, at least for these types of complex reasoning tasks. However, it's important to note that TTS didn't perform quite as well as models trained through knowledge distillation.
Ah, so knowledge distillation still holds the crown, at least for now. Can you remind me how knowledge distillation works?
Of course. It's like having a master chef teaching a student. You take a massive, powerful AI model and use its knowledge to train a smaller, more compact one.
So the smaller model learns from the best of the best.
Exactly. And because it's learning from a much larger and more complex model, it can often achieve surprisingly high levels of performance, even
Yeah.
surpassing what it could achieve through like direct training.
So it's like a shortcut to expertise.
In a way, yes. And it's been shown to be very effective for creating, smaller, more efficient models that can still handle complex tasks. However, knowledge distillation does have its limitations.
What kind of limitations?
Well, it requires access to that massive teacher model, which can be expensive and resource intensive, not to mention the computational power needed.
So it's not always a feasible option, especially for, smaller research teams or companies with limited resources.
That's right. And that's why research into, more accessible and efficient methods like compute optimal TTS is so important. It could democratize access to powerful AI, making it available to a wider range of users and applications.
That makes a lot of sense. So TTS might not be like the ultimate solution, but it's definitely a valuable tool in the AI developer's toolbox,
Yeah.
offering a balance of power and efficiency.
Precisely. And it's an active area of research. There's still so much we don't know about TTS and its full potential. Who knows what breakthroughs might be just around the corner?
Well, this has all been incredibly fascinating. I'm starting to see TTS as a kind of bridge between the world of massive, computationally expensive AI models and the need for more accessible, specialized AI solutions.
That's a great way to think about it, yeah. It's a way to balance the desire for power with the need for, practicality and efficiency.
Okay. Well, we've covered a lot of ground in this deep dive. I'm feeling both energized and slightly overwhelmed by all this new information.
I can relate to that. This paper is definitely a challenging one, even for those of us who spend our days, immersed in the world of AI.
But it's been a thrilling ride nonetheless, and I think we've managed to distill the key insights in a way that's both informative and engaging.
I hope so. We've explored the complexities of TTS, the limitations of PRMs, the importance of problem difficulty, and the potential for smaller AI models to challenge the status quo.
Well, we even ventured into the future, imagining a world where AI is more accessible, diverse, and beneficial for everyone.
Indeed, it's been a very thought-provoking conversation, and I have a feeling there's still, much more to discuss.
You're absolutely right. We've only just scratched the surface of this fascinating research. There are many more intriguing details and implications to explore, and I'm eager to delve even deeper.
I'm with you on that. Let's continue our journey into the world of compute optimal TTS and see where it leads us next.
Okay. On that note, let's summarize the key takeaways and the novel aspects of this research for our listeners today.
Well, this paper really challenges the notion that bigger is always better in AI development. Smaller models, when paired with efficient test time scaling strategies, can achieve comparable or even superior performance AI more accessible and efficient.
And the research also highlights the importance of choosing the right TTS method and understanding the potential biases of process reward models.
Right, and the authors introduced the concept of reward-aware TTS, which adapts to the specific PRM being used. And they emphasize the need to, carefully consider problem difficulty when designing TTS strategies.
Overall, this paper really pushes the boundaries of AI research and paves the way for more efficient and accessible AI systems in the future.
It's a must-read for anyone interested in the latest advancements in AI and the potential of smaller models to make a big impact.
Thank you for joining us on this deep dive into the world of test time scaling and the surprising power of smaller AI models. Until next time, stay curious and keep exploring.